In this video, we will look at two examples of some actual systems that we put together in the lab over the years. And they're very simple systems just to help us get some of these concepts in place. The first example is a heating system, just a temperature controller. And I've tried to map things out to make it as visual as possible. To see the relationships between, the process variable, the air signal, the proportional band, the output signal from the controller, the gain, and so on. So it's all kind of mapped out here. We'll try to go through it. A couple things to remember. Our textbook calls the process variable the controlled variable. So here it's designated as PV, process variable. There, our textbook uses that designation. Also, this DC is a duty cycle. We actually used duty cycle as a way to control the heating element. I put a little note here. It's the controller output signal. So the output signal could be other things as well, like a 4 to 20 milliamp signal, for example. Another thing I thought of to keep this as simple as possible for our first round of, putting all these relationships together. I put a note here. If we choose a range, also known as the span of the system, to be 100 degrees, that would actually be maybe say the system can go from 150 to 250 degrees. So we have a span of 100 degrees. What that does is then the proportional band can be designated in degrees or percent. They would be the same. Whether you refer to the proportional band in terms of how wide it is in terms of degrees or how wide it is in terms of percent of the range or the span, you can see they would be the same thing. If your span is 100, then that makes them the same. So I thought, let's do that for this opening example. So we'll say our system has a range of 150 to 250 degrees. We've chosen a set point for this example of 200 degrees. So that's right in the middle of the range. So we are trying to keep the system at 200 degrees. And you can see as the process variable varies, if it's under the set point, as in down here, the appropriate air signal is generated. So if I'm 1 degree under set point, an air signal of 1, 2 degrees under set point, air signal of 2, and so forth. If I'm over the set point, a negative air signal is generated. So if I'm 1 degree over, I get a -1 for my air signal, and so on. So those are all written out for us. Then as we move across the page, what we're trying to show is different widths of proportional band. You can see that each column represents a different value for proportional band. So if the proportional band would be 20, you can see maybe with the shaded areas here, this is all sort of shaded area, but let's take this first column. So my proportional band would be here. See the shaded area down to here. And the width of that proportional band is 20 degrees or 20% because we picked a range of 100 degrees. So, and you can see that, I think, look over here at the process variable. The proportional band is 20 degrees wide. So it goes 10 degrees in either direction, centered on the set point. So 200 down to 190, and then I'm out of the proportional band. Notice you can tell when you're outside the proportional band because look, 100% power is being applied. The duty cycle in this case would be 100% being applied to the heating element. But the control signal will be at 100% when you're below the set point end outside of the proportional band. So you can tell where the proportional band ends because you're at 100%. And in the other direction, our proportional band of 20 gives us 10% or 10 degrees in the other direction as well. So if you're above or over the set point, the proportional band will be decreasing the duty cycle, in this case, all the way down to 0. Once you're outside the proportional band, it's just off. And you can see it's when you hit 10 degrees above the set point, you're now from there on just going to be applying 0. Your control signal is a big 0, which is basically off outside the proportional band, or fully on outside the proportional band if you're below the set point. It's important to see that the controller output signal that varies from 0 to 100% is spread across the proportional band. That's probably the key to understanding the relationship between proportional band and gain. I'll say that again. The controller output signal that varies from 0 to 100 is spread across the proportional band. Pretty obvious when we have it drawn out like this, I think. So a proportional band that's 20 degrees wide spreads out the controller output signal that varies from 0 to 100%. It spreads it out over those 20 degrees. And look what that does. It means that for 1 degree change in the process variable, which is also 1 degree change in the error signal, so that you could think of it either way. But with a 1 degree change, what does that do? It causes a 5% change in the error signal, in the controller signal. And that is a look at gain. The fact that a 1 degree change causes a 5% change in the output signal, that's more of the perspective of gain. And of course, proportional band has this perspective. It's how wide are we in terms of encompassing the 0 to 100%. Proportional band and gain are inverses of each other. So maybe we'll work that out too on paper at some point mathematically, but here we're trying to do it sort of visually. Notice if I would change proportional band to a width of only 10 degrees, that would be, let's see right here. Can you see where the shaded areas are? Okay. I have cut the proportional band in half from 20 to 10. Visually very easy to see here. It narrows to half the width, right? And it would be half the percent of the span that it was before. So proportional band is cut in half. So now the controller signal that varies from 0 to 100% will vary from 0 to 100% in half the distance, right? So now each degree that the set point varies causes a 10% change in the controller output signal. Previously, with a wider proportional band, a 1 degree change in the process variable, the book calls it the controlled variable, but a 1 degree change caused a 5% change. Now that same 1 degree change in the process variable causes a 10% change from 50 to 40 in the output signal, the controller output signal. So here we would see that as a gain of 5, which now the gain is 10. The same change in process variable caused twice as much change in the output signal. It changed by 5%, now it changes by 10% for the same 1 degree change. the gain doubles when the proportional band halves. Cut the proportional band in half, or you could say you doubled the gain. Do you see how they're inversely related? You know. And as we continue across, you know, we just keep narrowing the proportional band and reducing that. So again, you know, now proportional band is just 8 degrees wide, or you could call it 8% since our span is 100. 6% or 6 degrees. Look here, proportional band has been cut all the way down to just 4% or also 4 degrees. Again, now let's compare proportional band and gain. Proportional band has been reduced to 4. Let's take the original proportional band of 20. So we are now sitting at 1/5 of where we were for proportional band. So if you reduce the proportional band to 1/5 of what it was, you can guess what gain should be. Gain should be 5 times what it was, right? To go down to 1/5 for proportional band should make gain go up 5 times. So gain should be 5 times greater. And let's see if it is. We can take our change in the process variable of 1 degree that used to cause a change of 5% in the controller output signal. Now it causes, that same 1 degree change in process variable causes a change of 25%, you know, in the output signal. When you go over temp by 1 degree, the controller output signal with a proportional band of 20, the proportional output signal will drop by 5%, trying to bring you back to the set point. If you have a narrow proportional band or high gain, look what happens. When your set point goes over by 1 degree, it's a more drastic effect. The controller signal will drop more drastically, all the way to 25%. It was at 50%, maintaining your set point. You went a little, the process variable went over temp. The output signal reacted pretty drastically. It cuts the signal all the way down to 25% when it was sitting at 50. If you make your proportional band very narrow, like this proportional band of 2 would be very narrow, or in other words, another way of saying that is crank up the gain, so very high, look what happens. If you turn up the gain too much or narrow the proportional band too much, you essentially come all the way back to just on-off control. Look what happens. The set point's at 200 degrees. If you go above the set point, oh, you just turn off. And if you go below the set point, oh, you turn on. 0% is off and 100% is fully on. So this is just back to on-off control. Above the set point, you turn off. Below the set point, you turn on. And that is what happens. If you crank up the gain too high, you're really hitting on-off operation, and it will oscillate. That's another basic concept to always have in your head. When we get to the chapter on tuning, it's just that simple idea that when you crank up the gain high enough, and you will cause oscillation, you're basically looking at a controller that's doing on-off control. In fact, when you are tuning a system, cranking up the gain to where it oscillates gives you good information. You can see the response time of the system, you know, how fast it responds, and you know, things like that, like its inertia and its thermal mass if it's a heating system and so on. That's valuable information. And one simplistic way of tuning would be to crank up the gain till it oscillates and then back off just under that point. That way you kind of have the best of both worlds. You have the tightest control without going into oscillation. So your proportional band is as narrow as it can. So it basically takes as drastic of action as it can to maintain your set point without spilling over into causing oscillation, where it's too drastic, so that the system's own inertia it causes these oscillations where you're kind of slamming it in one direction and the other too severely. So yeah, hopefully illustrates some concepts. You know, narrowing the proportional band does give you tighter control because the control signal is going to react more for a given change in the process variable. However, if you tighten up that control by narrowing the proportional band too much, you can start to get into oscillations. Of course, we can talk about that whole thing I just said in terms of gain. It's just you crank up the gain, but you have to be careful of cranking it up too much. We used the overtemp example to sort of zero in on. Of course, you could look on the other side of the set point as you were bringing the system up to temperature. We can look at that too. Kind of a nice review of proportional control in general. Let's say your system was cold, you hit the start button, so it's heating up. So below the set point, when you're outside of the proportional band and below the set point, you know, you're giving it 100% power. The control signal is at 100%, and now you just enter the proportional band here when your process variable, your system, gets to 190 degrees, you're exactly 10 degrees below the set point, which for a band of 20 degrees, you are now entering the proportional band. So what happens? You start to the control signal starts to throttle back. It starts to, you know, decrease to 95% when you're within 9 degrees of where you want to be. Now you're at 90% when you're within 8 degrees of where you want to be, and so on. So that plane coming in for a landing type thing, you're throttling back 85, 80, 75. You're now within 3 degrees, you know, so you're at 65%, and so on. When you're within 1 degree, you know, you're at 55%. And we had mentioned before, okay, you come into your set point and you're at 50%. Is that magic, or, you know, just luck, or what? But we did talk about having that as another topic. You would need to have some flexibility there to make sure that the controller output signal needs to match, you know, what it would take to maintain, in this case, the 200 degrees. So a lot of that comes down to sizing your system, you know, the actual sizing of the heating elements to the system itself. You wouldn't want to oversize or undersize the actual heating element. So those are other topics too. Maybe get to them in the future. But for our simplistic example here, you know, yes, 50% of controller output, you know, is exactly what we need to maintain our 200 degree temperature. And you mean you could make that work out. I mean, you could size things that way. Of course, you can see what happens if things try to go over temperature, like we mentioned before. Then the controller output's decreasing. For each degree that you're over temp, it'll cut back 5%. You know, and that's all for a proportional band of 20. Or you could also call that a gain of 5, right? Because for each 1% change in the process variable, 1 degree with a span of 100 is 1%. So we've got a 1% change in the process variable, also a 1% change in the error signal. but a 1% change in the process variable caused a 5% change in the controller output signal. That's a gain of 5. A 1% change in the process variable over here caused a 25% change, right? Yeah. So here we have a gain of 25, which is 5 times greater. And that makes sense because the proportional band is 5 times less. The inverse relationship should be apparent as you stare, the more you stare at this. Here at the bottom of this handout, we have a couple statements that help summarize. We did say, that the gain is really a measure of how much the error signal affects the control signal. In our textbook, maybe they talk about that as how much the process variable changes in the process variable affect the control signal. So that's fine. That's you could write that in for yourself. In other words, gain is a measure of how much a percent change in the process variable affects the percent change in the control signal. If you want to marry it right up to our textbook, how they talk about this. And yeah. Then we also see that inverse relationship. This statement is probably mostly true. And in the next example, you'll see that if you build sort of like a hardware dedicated controller type thing, you might have and especially in the older controllers that were more analog, there might be an actual potentiometer that controls the gain of an op amp. And, varying that pot turns the gain up or down, which widens or narrows the proportional band. So it's sort of that kind of cause and effect. You would adjust the gain in an analog controller in those days, and the proportional band would change. When we put this little system, this example together in the lab using a PLC, we weren't necessarily thinking in terms of varying a pot to control the gain of an op amp. It was just in the software. So we have our PLC program, and we can simply specify how wide the proportional band is right in the ladder program. So, and last on this page, here is an example of sort of what you get into once you understand the concepts. Then you still have to sort of put it all together in some kind of a math relationship. This is what we had to conjure up to create our little example program in the PLC. We said, well, the ultimate thing is we're going to have a controller output, a duty cycle generated. So what is that going to be determined by? It's going to be determined by the error signal, the proportional band, and then had to do some math here. So this is what we would actually use in a math function block in our PLC program. And coming up with, this actual math that takes what we were looking at above all spread out on a spreadsheet and reducing it to a math relationship. I think whenever I try to do that, it comes under that category of so simple it's hard, because you can, or at least I can, talk myself in circles, I find, when I'm trying to just deal with this, percent change, causing a percent change, and the percent change is the percent of the span, and then proportional band is also a percent of the span, but the change in the process variable is a percent of the span, and then you're dealing with, and then the final percent that you got to throw in there is the controller output varies from 0 to 100%. So you're dealing with this proportional band that's a percent of the span, and its width is what the 0 to 100% of the controller output divides itself up over. See what I mean? You can spend a little time trying to get that onto paper with accurate math relationships, not because it's super difficult math. It's actually frustratingly simple overlapping math with just percents and inverse relationships and just simple. But like I say, I don't know, maybe you'll have an easier time of it. I can definitely get myself going in circles sometimes and just have to stop for a minute, try to clear my head and go again. So this was the example of the little heating system we put together with a PLC. I'm going to stop the video here. I was originally thinking to put the servo example in with this video, but you know, it's gotten long enough once again, and as I think about it, that's probably not a good idea to just mash a look at a servo system right on top of this. Let's let the dust settle on this, and I'll put together a separate video just to talk us through maybe the little servo motor that we controlled in the lab.